All right, for today's lecture review, I'm going to be posting the final exam from last spring, which just a couple months ago actually. And we called this. I had two versions. I called it Mario and Luigi version. So this is the Mario version here. Very similar in content here, but I think that they will help us understand kind of what I'm expecting here. There's not a psychrometrics problem in here, but I think we've done enough psychrometrics problems. You should be well prepared for the exam that's coming on. So this one has a temperature and pressure of two ideal gases forming a mixture in an insulated mixing chamber are provided with the figure below. Considering constant specific heats, that's very important. Determine the temperature of the mixture at 3 and the entropy generated by mixing in kilowatts per Kelvin. Now, if this was not a constant specific heat problem, you would have to do some iteration, and that's not what I want to have happen. I don't want you to iterate if you don't have to. So, the first thing we want to figure out is what is the temperature of the mixture. And so that's going to be a first law analysis. So let's go down and look at that first law analysis. dE dt is equal to Q dot minus W dot plus the summation of my mass flow rates in, enthalpy in, kinetic energy in, potential energy in. Let me make my pen just a little bit finer here. Minus the summation of my mass flow rate xting times my enthalpy xting, my kinetic energy xting, and my potential energy xting. Okay. Now, in this case, we are going to have it at steady state. We are going to consider that it's adiabatic because that's what it told us in the problem statement. There's no power in this situation. No kinetic or potential energy effects as well. So all those things go away, and we're left with this. 0 is equal to, I don't like it that thin. We're just have to deal with a little thicker piece here. 0 is in it equal. Well, it's going to equal basically m dot ethane times enthalpy of the ethane at 1 plus the mass flow rate of my methane times the enthalpy of my methane at 2 plus the mass flow rate, minus the mass flow rate of my mixture times the enthalpy of my mixture at 3. Now, when we're doing with the mixture, we know the mixture is going to be basically both things that we've had there. So it's going to be the mass flow rate of the ethane at 3 times the enthalpy of the ethane at 3 plus the mass flow rate of my methane at 3 times the enthalpy of my methane at 3. Okay, so I'm going to write it simply as this. 0 is equal to the mass flow rate of my ethane times, because it's not going to change here, it's steady state, mass flow rate of my ethane times enthalpy of my ethane at 1 minus the enthalpy of my ethane at 3. And then we're going to have plus the mass flow rate of my methane times the enthalpy of my methane at 2 minus the enthalpy of my methane at 3. Okay, that's what we're dealing with. And now we're going to go with constant specific heats. And so we have 0 is equal to mass flow rate of my ethane times C sub P of my ethane times T1 minus T3 plus the mass flow rate of my methane times C sub P of my methane times T2 minus T3. Now, I provided you with C sub P's and C sub V's in this problem, so you could have to look at which one to use and understand that delta H is going to be C sub P delta T. That's what you need to understand here. And with this, we have all the rest of the information. We know the temperatures. We know the mass flow rates. Now it's basically a plug and chug problem that we're going to have here. So we're going to say 0 is equal to 6 kilograms per second times 1.7662 kilojoules per kilogram Kelvin times 15 minus T3. And I can leave those in Celsius because there's a delta T is the same in Kelvin as it is in Celsius. And then they go plus 3 times C sub P here is 2.2537 kilojoules per kilogram Kelvin. I should put here this is kilograms per second. Times here the T2, which is equal to 60, minus our T3. Okay, so now we're just going to do some algebra here. Now I'm going to skip the algebra steps because I think we should be comfortable with this algebra. And I'm going to tell you T3 is going to be equal to 32.53 degrees Celsius. That's what we're going to have for our temperature at 3. Okay? Again, all we're doing now is solving that equation, the first law equation, with a little algebra there. Now, the second thing this problem asks is it says find the entropy generated by mixing these two things together. So entropy generated, that's going to be second law. And so let's do here. ds dt is equal to, you want to see my bald head one last time. That's good. I can get in the frame. Is equal to the summation of the heat transfer rate over the temperature at which that heat transfer rate occurs, plus the summation of my mass flow rate in, entropy in, minus the summation of my mass flow rate exiting, entropy exiting, plus the entropy generated. Okay, and again, we're going to be dealing with steady state situation, and we're adiabatic. And so we're going to be down here to be this. 0 is equal to, and I can mimic this off of my first problem because I know I'm going to have that methane and ethane coming in together, and they're going to join into the mixture. And so it's really going to be the same kind of basically what we have in this step here for a bit. We're going to have mass flow rate of my ethane times H of my ethane at 1, sorry, not H, S, my entropy of my ethane at 1, minus the entropy of my ethane at 3, plus the mass flow rate of my methane times the entropy of my methane at 2, minus the entropy of my methane at 3, and then we're going to have plus sigma dot. Okay, plus sigma dot. Now we're using constant specific heat, so we now have to do our next step here and say, well, this is going to be equal to mass flow rate of my ethane times C sub P of my ethane times natural log of T3 all over T2, T3 over T1, sorry, T3 over T1, minus R natural log of P3 all over P1, okay? And this is all for our ethane here. Plus the mass flow rate of my methane times C sub P of my methane times the natural log of T3 over T2 minus R natural log of P3 all over P2, because now we're looking at just that methane, plus sigma dot, okay? And we could then, if we wanted to solve for sigma dot, and we'd have to get this thing all figured out here with the changes around. So we'd have to have sigma dot is equal to the subtract. We'd basically be subtracting all of this here if we wanted to do that. So and I've done this, you know what, I've done that already, and I'm sorry about that. I've done it in my head because I'm so used to it. But let's go here. If I were to do this the right way, would I do C sub P? I've been moving this. I moved this all the way ready over here to sigma dot, and this changes the order of these terms. This will be 3 minus 1, and 3 minus 2. Now, why do I know that I got that right? Because look here, when I do this C sub P, it should be final minus initial, and that's where that 3 minus 1. If I were left it in the earlier way I did it, I should have had 1 over 3, 1 over 3. So basically here, what I need to verify here, and because I kind of screwed up in here, whatever my numbers are here, 3 and 1, it's going to be, the first one is going to be the top, the second one's going to be the bottom. Okay, the first one's going to be the top, the second one's going to be the bottom, and my brain automatically went there, skipping a step, but I had it messed up algebraically, so I had to fix it. Okay, so that's where I want you to make sure that you can see what I've done and how I've messed this up a little bit. Okay, now we look at here and we're going to say, well, I need to figure out, I'm doing some things where I'm going to have to figure out what the mole fraction is, because when we come in here, the pressure at 1 and the pressure at 2 is a full pressure, but the pressure at 3 is going to be a partial pressure. So I have to calculate what the partial pressures are in order for us to do the calculation. So that means I need to figure out what is the molar flow rate of ethane. So that's going to be here, I said it was 6 kilograms per second. I know the molecular weight of that is going to be 330.07 kilogram per kilomole. And that tells me the molar flow rate is 1995, which was the year I was a junior in high school, kilomoles per second. And the molar flow rate of my methane is going to be, what we say here, we had 3 kilograms per second divided by its molecular weight, which is 16.04 kilogram per kilomole. And that's going to be 0.1870, which was a year that, I don't know, a lot of stuff happened back there in 1870. The Victorian era of England, I guess. Anyway, I think so. Victorian? I don't know. Which is the U.S. history. We're just coming out of the Civil War. It was just a mess. There's a lot of things going on in the world then and now and every time. But that's getting into a whole different class. Okay, so I want to figure out what the total amount of moles flowing is going to be. I'd have to add these two things together, and I get 0.3865. That's kilomoles per second. Now, so if I want to find the mole fraction of my ethane, I'm going to say what's equal to 1995.1995 over 0.3865. And that's going to give me 0.5162. And if my mole fraction of my methane is going to be equal to 0.1870, divide that by 0.3865, and I should get basically 1 minus my previous answer there, which is 0.4838. And if I were to add these two numbers together, I should get 1, and that's what I do. Okay, so I have to give myself a little bit more space here, and I'll start now plugging that into this equation here. I'm going to put this equation in here, and I'm going to say, okay, 0 is equal to the mass flow rate of my ethane, 6 kilograms per second. Now I could have done this in molar flow rate, but there's and you could. There's no problem with that. But I don't think there's any reason to do that in this problem. Okay, C sub P is equal to 1.7662 kilojoules per kilogram Kelvin. Natural log of my temperatures, which have to be in Kelvin. That have to be in Kelvin. You can't do them in Celsius. It has to be in Kelvin. So this is going to be my temperature 2, which I had 275, or temperature 3, 273, sorry, is going to be 305.53 Kelvin. So that's what I need to put there. So this is going to be 305.53 divided by my original temperature, which it was 15 plus 273, which is going to be equal to 288. And this is plus 273. This is going to be equal to 333. Okay, so let's put those numbers down here. So 305 divided by 288. Then it's going to be minus R, which is going to be 8.314 divided by the molecular weight of my ethane, which is 30.07. Natural log of my P2 over my P1, or my P3 over my P1 here, which is going to be 0.5162 times the pressure there was 1 bar. It was 1 bar all over 1 bar. Okay? And then we're going to have to add to that plus 3 kilograms per second times 2 point, the 2.2537 kilojoules per kilogram Kelvin, times the natural log of 305.53 divided by 333. And then we're going to have minus 8.314, but now we'll have to do this as the R value of my methane, so I have to divide this by 16.04, and this is going to give me kilojoules per kilogram Kelvin. Natural log of now 0.4838 times my pressure at 1, divided by my total pressure there at the very beginning. Notice this partial pressure, total pressure thing is important for you to understand why that's the case, because we are mixing something. It's coming in as two separate streams coming out as a mixture. That changes things completely. And when we find what our sigma dot is going to be, it's going to be 2.2701 kilowatts per Kelvin. Okay. Good problem, long problem. Touches on mixing of ideal gases. Must understand what we're doing there. to be successful. A problem like this is you've seen it on other practice exams involving mole fraction, all that good thing here. Again, this is doing constant specific heat. If we're doing a variable specific heat problem, how would we solve it? These are all things that I'm going to make sure that you know when you talk about ideal gas mixture. So you're going to have either an open or closed system ideal gas mixture. I promise you there's going to be only 2 things mixing in it, not 3 or 4 or 5. You need to know about mole fraction, mass fraction, how all those equations work, how can you manipulate those, and then you'll be fine on your first, on your ideal gas mixture problem. We'll stop there and move on to our next problem.